afternoon, everyone. I'm Bhishek, a fourth year PhD student in the Applied Maths department over here at UCSC Cruz. I'll be talking about formation of X-ray rotating jets in solar corona, simulations and observations. So this is the work which I've been doing at Boulder, Colorado, with my collaborators Yong Fan and Frank Fan. And this is part of my PhD, which I'm doing with Nicholas Brummel over here at UC Santa Cruz. So let's get started. What you see over here in the screen is 3 images. The first one is of solar corona. What is solar corona? Solar corona is basically the picture of sun that we see during total solar eclipse. So the outer bright region that you see over here in the first image, that's basically the outer solar atmosphere, which is known as the solar corona. And it's a region of very high dynamic activity. When we look at sun from Earth, we don't see it to be as dynamic as what we see from really close by using space observatories or even some ground observatories. The second image that you see is solar active regions. Why are they called active regions? Because these bright regions that you see in the second image, the central image, are magnetically active, and what they represent is regions where really high dynamic activity like solar flares or some other high energetic activities take on. The third image is of coronal loops. These are basically magnetic loops that we see from close by when we look at the sun sun very closely. These are basically magnetic fields poking out of sun, forming a loop and going back in, and they are really high magnetic, so they have really high magnetic activity. Now, for my work, what I do is we look at these coronal loops, these active regions, because they are the source of really high magnetic energy production, like really high explosive events occurring on the sun's surface. What you see in the first image over here is jet formation and jet eruption. What are jets? They are basically high magnetic energy events occurring on sun's surface, which basically throw out lots of plasma from the sun's surface. Plasma is basically just electrons and ions moving at high speed. Now in the first image at t equals to t1, what you see is this magnetic flux basically emerging from the interior of the sun and emerging at the solar surface. The second image shows an arcade-like structure that forms, and by some physical processes, there's instabilities in this magnetic region, and we have this jet formation. So you have this really high energetic hollow rotating jet that goes away. I'll talk about how this happens. So what we see observationally, like looking at observations, what we see is beam-like structures, collimated beam-like structures which eject high energy plasmas, and they emit in ultraviolet and X-rays. Some of the observations that tell us the basic characteristics, like this time scale of 10 minutes, these events occur in like 10 minutes. The width and the height are like in tens of thousands of kilometers. The speed with which the plasma flows is hundreds of kilometers per second. The way we model these events is by very simple structures like there's of like in the theory section, you can see there's the second image which shows something called magnetic reconnection going on. Magnetic reconnection is a basic physics process which says that if you have two oppositely directed magnetic fields and they are close together, they can lead to very explosive events by restructuring of those field lines if they come very close together. Now, we do a simulation in three-dimensional Cartesian units where we have a magnetic flux tube which rises from below the surface of the sun, emerges at the solar surface, interacts with the outer field, and leads to the formation of this high energetic solar jets. Now you see a bunch of complicated equations, but these represent the basic physics principles that we know of. The first equation is just mass conservation. The second equation is Newton's second law of motion. The third equation basically says that your plasma or your electrons and ions move along the magnetic field lines. The fourth equation says that there's no magnetic monopoles in our universe. The fifth equation basically says there's energy balance. So you have the first term which shows that there's energy due to moving of electrons and ions, so the kinetic energy. There's magnetic energy. There's other physical processes that go on in the sun's surface that we try to model. And the sixth equation is the ideal gas law, basically the law that the gas molecules follow. The first image that we have, that's our initial condition setup where we have a magnetic flux tube. So these are basically coiled in magnetic field lines which are twisted, which emerge from below the surface, and the blue surface that you see is basically the sun's surface. So these magnetic field lines emerge from the surface, and they then lead to the formation of jets. The second image is basically how the pressure, density, temperature, magnetic pressure vary as a function of height. So these are basically our model input parameters. Some results that we have, preliminary results, is that the first image that you see, the rotating one, that's basically how the magnetic field structure looks after evolution in our simulations. So what we see is that the magnetic field lines, they have a very strong correlation with the observation. So we are able to reproduce at least physical structure, which is very similar to what we see from observations. Some of the physical parameters that we measure in our simulations, like the size of this jet formation or the velocity with which this jet erupts and the plasma flows out, is very much correlated with the observations too. So on the zeroth level, basically, we are able to model a solar jet eruption. Also, I don't mean to impress that this is actually what goes on in the sun, but this is one of the possibilities because the sun is so complicated and we are not aware of so many physical processes. This one, so we are able to do fairly well as a one particular scenario. The field lines, what you see, the color basically represents how the temperature varies. So what you see over here in these long field lines is the red color, right? So that represents billions of Kelvin of temperature that we see in this region. This is the region where the magnetic field lines basically break apart and the magnetic reconnection phenomena happens in strong jet forms. Some future work that I intend to do with this is I need to understand how the energy gets transported from below the surface of the sun to the solar corona. There's another observations that we see is that these jet eruptions happen, like there's not just one jet eruption, but there's multiple jet eruptions going on. So we have to model that in some way. Why is this work important? This work is important because we, first of all, understand the basic physics that goes on at the surface of sun of really high energetic events, and also this has implications in our understanding of space weather. Space weather is basically the field that that talks about how these high energetic phenomena on the surface of sun affect us on Earth. The second image is the synthetic X-ray emission that we get out of these simulations. So the second image is not observations, but we can pretty much regenerate structures which look very much like observations.